Welcome to today's class where we are going to deal with current and electric circuit. So in our previous lessons, we already talked about charges. We already talked about electric field, region around a charge where electric force can be felt. So, but charges are not useful when they are static. So what we did last class is static electricity. But when charges are moving, that's what we call current. The rate at which charges flow is what we call current. And this current, they are very useful in electricity, in what we call electrical energy, to power, motor, like fans, and also to convert electrical energy to light energy, like electric bulbs, and also to convert electrical energy to heat energy, like your electric iron and the likes. So the first question is, what is electric current? So electric current, which sometimes we just call current, symbol I, is the rate at which charges flow. Rate of flow of charges is called electric current. Rate of flow of charge. So this Q is quantity of charge in coulombs. This T is time in seconds. So we can say that the unit of current is coulomb per seconds. Coulomb per seconds. And this coulomb per second is also called amperes. So amperes. So when I ask, what is 1 ampere? So 1 ampere is the current that flows when a charge of 1 coulomb moves in 1 second. And from there, if we cross multiply, we get that quantity of charge is electric current multiplied by time. Q equals to IT. Let's take this as equation 1. Now, current by convention is taken to be positive. But we know that the charge that's actually flowing is electron. Suppose this is a conductor. Inside this conductor, we have electrons. But those electrons are embedded. They are not actually moving in a cycle. They are not moving in a cycle. They are dead. So for us to have current, these electrons must move in a cycle. So you have what we call electric cycles. So in a circuit, these electrons, they need to flow, to keep flowing. So when these electrons are flowing, then you say current, there is current. But if it's not moving, there is no current. So the question is, for this electron to move, according to Newton's first law of motion, a body will never move until there is an external force that moves it. So these electrons here will not move. So a force is needed to move the electrons. Electromotive force. So that's the force required to drive electrons around a circuit for us to have what we call electric current. So we have different sources of EMF, electromotive force. One of it are what we call electric cells. So electric cells, and the symbol for electric cell, when it's seen like this is an electric cell. This is the positive terminal, the negative terminal. So what does electric cells do? They create what we call potential difference. Whenever there is a potential difference, hence current to flow. First, cell as source of EMF, electromotive force that moves electron. And how do they do that? By creating what we call potential difference. So I ask you, what is potential difference, V? So it is actually the work done in moving a unit charge. The work done in moving a unit charge. Or you can say is the work done per unit charge. So to move a charge from this point to this point, from this point to this point, the work you have to do per every charge move from this point to this point is what we call potential difference. And from here, if we cross multiply, or the unit of work done is joules, charge is coulomb. So joules per coulomb, which has another name, we call it volt. So that's what is 1 volt. You see, 1 volt is the potential difference. When a work of 1 joule is done to move a charge from one point to another. So that is 1 volt. And from here, if we cross multiply, we get that work done equals to QV. Let's take that as equation 2. Let me give you an analogy to understand this better. Suppose we have a bowl held vertically upward, from the ground, and inside this bowl we have water to this level. Consider the molecules of this water as electrons, the charge down to flow. Now, for this water to flow, there must be potential difference. What do you mean by that? We know what called potential energy, mgh. The height of this point from the ground and this point is the same, so they are at the same potential. There is no potential difference. For there to be different, there must be a motion. This thing has to be tilted. When you tilt this thing this way, what happens? The water will start flowing. So this water will flow after being tilted. Why? Because the potential here and the potential here, they are different. So this water flowing are the what? Charges. Your hand to move this thing is like the source of the EMF that moves the electrons. So the more you tilt it, the more the water flow out. So before electrons can flow, there must be potential difference. I was saying something about current being positive. Current is taken to be positive, but what's actually flowing is electron. So note, if electrons are flowing from this point to this point, these are the charges electrons from here to here, then the direction of current is actually from this point to this point. Current has taken to be movement of positive charge. What actually moves are electrons. So when electron flows this way, current flows the other way. Note that. Now, when a body slides on a surface, we call something friction. When the body slides on another body, there is friction. What makes electron to move is V, potential difference from cells. What is actually flowing is current, I. But there is something opposing the flow of current, and we call it resistance. To understand what resistance means, you have to go to what we call Ohm's law. So Ohm's law states that the current flowing through a metallic conductor, the current passing through a metallic conductor is proportional to the potential difference across its end. To the potential difference across this end, to create a potential difference in a wire, we are going to put what? Battery there, or a cell. Once cell is put there, it will create a potential difference. This is the high potential and low potential. So current flows from negative terminal to positive terminal, although electron flows from the positive to negative. So this takes the direction of current. So anytime we have a cell, if the cell is drawn this way, the direction of current is here. This is I. If the cell is drawn this way, the direction of current is this. Current always flow from negative terminal to positive terminal, but electrons opposite. So Ohm's law, the current passing through a metallic conductor is proportional to the potential difference across its ends, provided that temperature, cross-sectional area, and other physical factors are kept constant. So from here, V becomes Ki. This constant is what we call electrical resistance or electric resistance. Resistance can also be mechanical, which is like friction. So for me, you can say V equals to Ri, but it's mostly like it's most time written as V equals to IR. This is adapted from Ohm's law. Ohm's law, V equals to IR. So our third equation. Now what is R from here? R equals to V over I. The unit of potential difference, this V means potential difference. The unit is volts. And the current is amperes. That's volts per amperes. So this volts per amperes has a name. We call it ohms. Ohms. This is symbol for ohms. R is V over I. So for every metal or every conductor, what are conductors? They are solid. They allow current to pass through them easily. Non-conductors, they do not allow current to flow through them easily. So for every conductor, they have what we call electric resistance. They have what we call resistance to flow of current. And there are many factors that affect the resistance of a conductor. The first factor is the length of the conductor. The longer the length of the conductor, the more the electrical resistance. So resistance is directly proportional to the length of the conductor. So if you have a long conductor and a short one of same area, that longer one has more opposition to the flow of current. Current will not pass through it easily. Secondly is the cross-sectional area. Not just area, the cross-sectional area of the conductor, written as A. And the resistance of a conductor is inversely proportional to the cross-sectional area. For this first part, I have this conductor and this conductor. So the longer one will resist flow of current more. Second one, cross-sectional area. If we have this conductor this way, this is like cylindrical, and this one, they have equal length. This one will resist flow of current more. For this one, it will allow current to pass through easily. When we say cross-sectional area, we are talking about the area of the base. It is a prism. So in this case, this area is area of a circle. So our A here is actually pi r squared. In terms of diameter, pi b squared over 4. So that's the cross-sectional area. So if we combine this together, it means resistance is proportional to length inversely to area. Then our R equals to a constant comes in, symbol rho. The symbol is rho. And if you make that rho the subject, rho equals to RA over L. So that rho is a constant. Every material, they have a constant value for rho. And that rho stands for what we call resistivity. Resistivity. Resistivity is the ability of a conductor to oppose, the flow of current. So the more the area, the more the resistivity. The more the length, the lower the resistivity. So resistivity is RA over L, if you make the subject there. The inverse of resistivity is what we call conductivity. The inverse of resistivity is what we call conductivity. So conductivity, this symbol, is called conductivity. And they are inversely. So conductivity is the reciprocal of resistivity, inverse of each other. And from here, we can actually get the unit of resistivity. This is ohms, this is meter squared, this is meter. So meter will cancel meter squared, we are left to meter here. Meter times ohm, that's ohm meter. So the unit of resistivity is ohm meter. So these are the factors that affect the resistance of a conductor. The third one is temperature. Temperature. If we have hot wire and cold wire will conduct more than hot wire. Why? Resistance of a conductor increases with what? Increase the temperature. As temperature increases, resistance will increase. Why? We can explain molecularly, or we can even move to thermal physics. We know that for a conductor of length L, if the temperature increases, the length will increase. The length of metals increases whenever there is increased temperature. That's what we call thermal expansion, or we call linear expansivity. So if the length increases, what happens? R2 will increase. So indirectly, if temperature increases, resistance must increase because the length will increase. Then the fourth factor is nature of the conductor. Nature of the conductor. To understand this, you have to go and look into chemistry. So if you have two conductors, let's say iron and copper, they have equal length, they have equal diameter, and they are the same temperature. Two conductors of equal length, equal cross-sectional area, they have same temperature, their resistance will still be different because of their nature. For example, metals from group 1, when you go to periodic table, in group 1 we have sodium, we have potassium and the likes. When we go to group 3 we have aluminium as you go down. So if you compare aluminium and potassium, they are both at second energy level. Potassium has lower ionization energy, meaning it can easily what? Give out the electrons. So meaning the electrons at the surface of potassium, they are more loosely bounded compared to aluminium. So what happens? It means the electron will flow easily when we have what? Potassium. So those in group 1 will be better conductors compared to elements in group 2 and group 3. So that is about the nature of the conductor. So these are the factors that affect the resistance of a conductor. Before we move on, let's summarize all the formulas we've gotten so far. So 1, we have 2, we have 3, we have 4, and we have 5. You should know what each symbol stands for. Definition and units. This is Q, quantity of charge, coulombs. Current, amperes. Time, seconds. Work done, joules. Charge, coulombs. PD, potential difference, volts. Potential difference, volts. Current, amperes. Resistance, ohms. Resistivity, ohm meter. Resistance, ohms. Area, square meter. Length, meter. Conductivity per ohm per meter. Resistivity, ohm meter. I should know what each stands for. Now, let's move on. Electrical energy. Whenever current flows through a metallic conductor, after some time we notice that it becomes hot. The temperature will increase. So heat energy is generated. And how can we get that? The heat developed in the conductor. So that is just its loss. Now let's go back to work done. When work is done, energy is what? Transferred. From what does the work to what we receive the work. So work done and energy, they are equivalent. So I can say energy equals to QV. But in electricity, most likely we don't talk about charges. We talk about charges small in electrostatics. So that is why I'm going to replace Q with I. What's Q? IT from here. So from here we can say E equals to, instead of writing Q, I'll put IT there times V. So then from there E equals to IVT. But most times we like to express the energy in terms of resistance. If we come here, V is IR. We could have stopped here, but because V is IR, we can replace this V with IR. And in doing so, I have I here, I have T here. Replace V with IR, you put IR here. So I times I is I squared. So from here it means E equals to I squared RT. This is another formula for what? Electrical energy. And actually this is what we actually normally use. The more the resistance of a conductor, the more the heat energy that will be developed. So call something just its law of electrical conductor. It says the heat developed in the conductor is proportional to the square of the current passing through it and its what? Resistance. Okay, here we don't have R, here we don't have V. Let's get a formula without I. From here, if you make I the subject, I equals to V over R. Since I equals to V over R from Ohm's law, we can come here and replace this I here with V over R. Originally we have E equals to IVT. Then from here we can say equals to, replace this I with V over R, that will be V over R, then VT. So if we multiply V times V, we get what? V squared. So equals to V squared over R times T. Another formula for electrical energy. Note, this is the foundation. From here, we got this, we came here, making 4. Then in terms of electrical power, we know that power, P, is what? Rate of what? Work done, or rate at which energy is expended. From here, if you multiply, energy goes to what? PT, energy in form of power. So in total, we can say electrical energy, in terms of charge, is QV. In terms of power, it is PT. In terms of current and voltage, it is what? IVT. In terms of current and resistance, it is I squared RT. In terms of voltage and resistance, it is V squared over RT. So all these are the possible formulas to calculate electrical energy. So all these forms are used, but the one we should focus more on is this, Joule's heat loss, because we can get some parameters directly. Why this one? We are not going to deal with it most very as much until we get to atomic physics. So when you are looking in physics in microscopic level, so there we replace this quantity of charge with what? E, charge on an electron. Like I said, when we talk about charge, we are mainly dealing about with electrons. So in that case, we'll be using our energy to be what? EV. So it's from this QV. So this quantity of charge, this is what? This is what? Quantity of charge on an electron, EV. So but these are the ones you use most times. Especially these three: IVT, I squared RT, V squared over RT. So the formula you're going to use depends on what you are given and what you are looking for. Okay. Power, general definition of power is energy over time. We know that energy, let's go back to power. So power is energy over time. Energy is joules, time is seconds, that's joules per seconds. Joules per second is also known as what? Watt. So note, the SI unit of power is watt. And what is power? Power is gotten by dividing energy by time. So we can come here. Let's divide everything here through by T. PT over T will give us P. IUT over T will give us IV. I square R T over T give us I square R. Just remove T, you get power. So these are the possible formulas to calculate what? Electrical power. Electrical power. So the unit of energy is joules. Unit of power is watt. Electrical energy, electrical power. Next, let's look into cost of electricity. That's buying and selling of electrical energy. So electrical energy is usually sold in a particular unit. So the unit of electrical energy is actually joules, yes. But under buying and selling, what we use to calculate the unit, 1 unit of electricity is PT. That's power times time. So power is watts, time is seconds. So it means watt seconds is also joules. Yes, it's also joules. Because it's the same formula for energy. But under power consumption, for example, at home, you can have electric fan rated 200 watts, electric iron rated 1.2 kilowatts. You can have your freezer rated, let's say, 800 watts, your washing machine rated 650 watts. So at home, you can always get the total power of all the electrical gadgets you have. So and the power is usually high when you leave it in watts. So most times the power will be converted to kilowatts. And when you are using those appliances, you don't use them for seconds or minutes, you use them for hours, even sometimes days. Some people, they can put on their freezers for several days without putting it off. So in that case, the time, we don't use seconds again, we use what? The time in hour. So that makes 1 unit of electricity to be sold in what? Kilowatt hour. 1 unit of electricity is in what? So it can be told that that small c represents the cost of 1 unit. Cost of 1 unit of electricity. It means 1 kilowatt hour will cost what? Small c. So now, this is what you have here. First, we must convert everything to kilowatts. So this 200 in kilowatts over 1000, 0.2. This already in kilowatts, 1.2 kilowatts. This one over 1000, 0.8 kilowatts. This one over 1000 give us 0.65 kilowatts. If you add everything here, we are going to get the total power in kilowatts. Total power in kilowatts. If you press your calculator, you should get. Okay, so let's suppose these are all the electrical appliances you have in your house. So this is total power. So we want to get the cost of running all those appliances for, let's say, a whole day. For a whole day, that time for a whole day is 24 hours because time was being an hour. So we can get your total power consumption or your total energy rather, total energy. So this 1 kilowatt hour is energy. This 1 unit to be C. So total energy will now be what? Let's call it capital C, or let me consider it as total cost. So if multiply total cost times 1 is total cost. So for me, it means total cost times 1 equals to, let's call it total energy times small c. Why small c is cost of what? Cost per kilowatt hour. And how do we get to that time? We multiply this with this. So total energy equals to total power times total time, which is what? 2.85 kilowatts times 24 hours. So if you do 2.85 times 24, you get 68.4 kilowatt hours. So this is total energy. So now you can now calculate our total cost. Or in short, we can say total cost equals to total energy. How do you get total energy? Total power in kilowatts times total time in hour, then times the unit of electricity, small c, that's cost per watt. Cost per. So let's suppose in a particular place where the cost per kilowatt hour is, let's say, 5 naira. If the cost per unit or the cost per kilowatt hour, small c, is 5 naira, and this is your total energy consumed in a day, so we can calculate total cost per day. So total cost in this case will give us total energy here 68.4 times the cost, which is 5, and that will be 342 naira. So it means every day you'll be spending what? 342 naira to run all those appliances if you have to put them on for 24 hours. So in a month, in 10 days, that will be 3,420, and in a month you'll be spending over 10,000 naira. So normally when you see 342 naira, you think it's small, but you multiply by 30 days, that's over 10,000 naira already. And the cost per kilowatt hour differs from place to place. If you're in band A, their own cost can be 10 naira. So meaning at the end of the day, you spend about 20,000 naira for all these appliances. But the thing is, most likely you're not using them for the whole 24 hours. So there's a way you calculate the average power. But that's not for this class. But with this little explanation, I believe you can deal with any question that is with buying and selling of electrical energy. First thing is to get total power. It must be in kilowatts. So if your answer is in watts, divide by 1,000. Your time is given in days, bring it back to hours. If it's in minutes, convert to hours. Then multiply total power in kilowatts, total time in hours, you get total energy. So multiply total energy by the cost, or total power, total time in hours times cost per kilowatt hour, then you get total cost for that period. So a large degree, I believe we know what current is in a very large degree now. So let's come to electric circuits. Now, what is electric circuits? When we have a path, an enclosed path, where current can flow continuously, we call it electric circuit. In an electric circuit, to move current, we need what? Source of PD. Yes, current have to flow. Then we need a key to close and open the circuit. Then we need the load, what is actually what? Consuming the current. Whether it is fan or it is bulb or iron. This is the simplest way of representing an electric circuit. We have the source of PD, we have the key to close or open. If we have something like this, if this is pressed down, then this is what we call a closed circuit. And in a closed circuit, current will flow. But if the key is like this is open circuit. In a closed circuit, current flows. In open circuit, current doesn't flow. Then we have the last one, we call it short circuit, but we are not doing that one now. So here we have source of PD here, or source of EMF, to create potential difference between this end, so current can flow. So once the key is closed, current will flow from where? The negative terminal, the short one, to the positive terminal. So this is the direction of flow of current. And the reason current will not flow if it's open is because when it gets here, there is no connection. It's not an enclosed path again. So this is what? Open circuit. Now let's close the circuit. Now this R represents, sometimes you can call it load. What is consuming the electrical energy? It can be fan, it can be your freezer, it can be your electric iron and the likes. Then we have another electrical device which we call a fuse. For example, let's suppose this is your television. So this is your television, it has maximum current it can take. So in order to reduce the current that will get to it, or in order for this not to be destroyed by high PD or high current, So a fuse is going to be what? Connected to it. Sometimes what enters the house, from the source, from the transformer. So there will be electrical energy to the building. So when it enters the building, before it is distributed to the apartment, we have a fuse. So that fuse is mainly to control the amount of current that enters. When the current is beyond what is expected, the fuse is going to get burnt. It's like a conductor that is very fragile. Yes, very fragile. So when the current is too much, it's going to melt. And when it melts, it breaks or it's cut. The open current will not flow into the building again. So that's function of a fuse. But that is business for another day. So here we have just a single load. So according to Ohm's law, what let VIR is what? V equals to IR from Ohm's law. If you sketch the graph of the voltage here against the current, you get a straight line graph start from the origin. When you take the slope of this graph, slope of a graph means the change in vertical axis, which is change in voltage or PD, to the change in horizontal axis. That is slope. So here the slope is what? V over I. And what is V over I from here? R. It represents the what? The resistance. If you sketch V to I. But if you sketch I to V, the slope will inverse of resistance, which is called conductance. But that is not where we are going today. So this is brief about electric circuit. But this is a simple circuit you can have. Why sometimes in a simple circuit you can have 2, 3, 4, 5 loads. And these loads, they can be connected in both series and parallel. That will take us to the series and parallel arrangement of resistors. So this is what we call a resistor. So let's start with series arrangement. For series arrangement, all the resistors are connected between the terminals of the cell. Everything in between the terminal of the cell. So let's say this is a cell. So between this terminal, we can have several resistors here. So this is what we call series arrangement. Then this end will be connected to this. This end is also what? Connected to this. So let's call this one R1, R2, R3. So total PD here is V. So if total voltage is, let's say, 50 volts, or let's say 60 volts, that 60 volts will be shared between these two resistors. And even they have equal resistance. And this one is 60 volts, they will take 20, 20, 20. So the voltage across the first one, let's call it V1, this one V2, this one V3. So the total PD across the whole circuit is what? V1 plus V2 plus V3. These are called Kirchhoff voltage law. According to Ohm's law, V is IR. So this is total V, let me call it VT. So total V can be written as I total, R total. V1 can be written as what? I1 V1, V2 I2 V2, V3, R rather. V1 is I1 R1, V2 is I2 R2, V3 is I3 R3. But note this. When resistors are in series, the same current flows through them. So if the current here is 2 amperes, what pass through R3 will be 2, R2 2 amperes, R1 2 amperes, it will come back here. So it means the total current in the circuit, I total, equals to what? I1 equals to I2 equals to I3. They all have equal what? Current. Total current is not splitted. So let's call everything I. So I can come and replace this I total with what? I R total equals to I R1 plus I R2 plus I R3. Then from here I have I R total equals to I is common. If you factorize I, we have R1 plus R2 plus R3, and from here this I cancels this I. So it means if you have resistors in series, the effective resistance is the sum of the resistance of every resistance. Even if you are more than 3, you keep adding. So that is what? Effective resistance, or the total resistance, or sometimes they call it resultant resistance. Now, the series arrangement sometimes might not be like this. This one that is here, we can also put it here too, and put it here. It is still series arrangement. Let me redraw this. This and this, they are the same. This is still series arrangement. Because if I remove this battery, I can spread it in horizontal this way. It will be like this. Or this one, from here, I can bend this one down this way. So this is still series arrangement. Then let's move to parallel arrangement of resistors. Now, these are three resistors, R1, R2, R3. So in parallel arrangement, all these terminals will join together, all these two will join together. So then you can join a straight line, or you can have something like this to form what we call a node. So this parallel arrangement. And here, between here, you can now put a cell, electric cell here. So this is parallel arrangement. Note, they are all between same potential. So the PD across R1, R2, and R3 will be the same. So the PD across one is V, this one is V, this one is V. For series, if one is coming out is I, what will pass through R3 is I, R2 is I, R1 is I. So same current, different PD. This one, same PD, different current. Suppose the current that comes out from here is I. When the current gets here, it will split into three. Some will go here, some will go here, and some will go here. Let's go this one I1, that will go to R1. This one I2, that will go to I2, R2, and this one I3, that will go to what? R3. So in this case, the current is split into three. So the total current I equals to I1 plus I2 plus I3. And this is what we call Kirchhoff current law. So for parallel, we add current to get total. For series, we add voltage to get total. Then from here, from Ohm's law, V is IR. If you make I the solid from here, you make I the solid, I equals to V over R. So you can come here and replace I, this I with what? V over what? Total R. Then this I1 is what? V over what? R1. I2, V over R2. V over what? R3. And as you can see, V is common all through. So we can bring out this V and everything can cut out. And from there, at the end, if you make RT the subject, we are going to get the effective resistance RT to be equals to 1 over R1 plus 1 over R2 plus 1 over R3. That will be the what? Total resistance for this case. So for series arrangement, we just add. For parallel arrangement, we take the reciprocal of the sum of the reciprocal of the resistance of each resistor. And note, the circuit for parallel arrangement is not always going to be like this. You can also have another arrangement. Let me draw it here. All these three are still in parallel. So this is the node, the common node to them. Common node to them. To the terminal of this cell. So they are in parallel. Then it can also be drawn this way also. All these three are still in parallel. So it can look like this, or like this. For series, it can look like this or like this. And in some question, they can combine both parallel and series arrangement. So you should be able to identify series from parallel. If you have series, you should know it's series. If you have parallel, you should know it is parallel. Before moving to hybrid circuits, where we have both series and parallel, let's talk about voltage divider rule between two resistors in series. Let me even explain it. Okay, we'll do that now. Suppose we have this simple circuit and it produces a current I. According to Ohm's law, total V equals to I times total R. Now what is total R? Since they are in series, total R equals to R1 plus R2. So from here, we can say V equals to I. What's total R from here? R1 plus R2. And we make this I the subject, R equals to V over R1 plus R2. So this is total current flowing. Since they are in series, the current that will flow through R2 is I. R1 is also I. They are in series, same current pass through them. So our aim is to know the voltage across R1 and voltage across R2. What is V1? V in general is IR, so that will be I1, R1. But the I is constant. And what's V2 also? That's I2, R2, but the I is the same. So from there we can say V1 equals to, what is I? This is I now. V into R1 plus R2 times R1. Same for V2. What is I? I is what? V over R1 plus R2, R2. So we can write this as V1 equals to R1 over R1 plus R2 times V. And V2 equals to R2, this one over the whole of this, R1 plus R2 times V. These are called voltage divider rule. Suppose total voltage in that circuit V is 20 volts and R1 is 2 ohms and R2 is 3 ohms. What will be V1? What will be V2? That is the importance of this voltage divider. So these 20 volts we share between R1 and R2. There will be a voltage drop across R1 and R2. How do we get that? From here, V1 equals to R1. What is R1? 2 over R1 plus R2. 2 plus 3, 5. Then times V. What is V? 20. So what is V2? V2 is R2. What is R2? 3 ohms over 5 times 20. From here, it means V1 equals to 5 in 24, 4 times 2, 8 volts. Same goes here, V2 equals to 5 in 24, 4 times 3, 12 volts. So meaning, if we have 2 resistors, and one is 3 ohms, the other is 2 ohms, they will share 20 volts in this manner. So, what we did here, 2 ohms, 3 ohms. This 20 volts will be shared by them. The one that has 2 ohms will take 8 volts. The one with 12 ohms will take what? With 3 ohms will take what? 12 volts. Making together 20 volts. Meaning the resistor with higher resistance will have more voltage drop. So the one with lower resistance will have what? Lesser voltage drop. This voltage divider rule for series arrangement of 2 resistors. Then another shortcut you have to know, if we have 2 resistors in parallel, only 2 in parallel. Suppose we have these 2 resistors in parallel. According to the formula, the effective resistance R total equals to 1 over R1 plus 1 over R2. So we want to generate a quick formula. So that's 1 over, the LCM of R1, R2 is R1 times R2 over, so R2 in this give us R1, R1 times 1 is R1, plus same thing here, R1 here, R2 times 1, R2. So this inverse, meaning our R total becomes R1, R2 over R1 plus R2. So if we have 2 resistors in parallel, we don't need to use the formula again. So we can just directly multiply, then divide by the sum. For example, here, we have 2 resistors in parallel. You might be wondering, why this symbol? Resistor actually has 2 symbols. So the first one is one we used before, this. And we also have this. So these 2, we can use them for the symbol of resistor. In fact, we have another one like this. When we have this symbol, it means this is a resistor whose value can be changed. It is called a variable resistor. A variable resistor. A resistor whose value can be changed. So now we have 2 resistors in parallel now. So instead of being 1 over 1 over 4 plus 1 over 8. Very quick, using this formula. Since they are in parallel, we what? We multiply. So we do 4 times 8, that is 32. Then we do 4 plus 8, that is 12. Finish. You can cut to the last bit. So if you have 2 resistors in parallel, you don't need to follow this approach. Multiply the 2, then over add the 2. If you cut this, you first get 16 over 6, you get 8 over 3 ohms. What if you now have both series and parallel arrangement? How do you do that? Very simple. Now look at these two examples. If you check very well, you notice that these 2 and 3, they are in series. Although it looks as though they are in parallel, they are not in parallel. If they are in parallel, these 2 ends will be connected to a node, to a battery. But it doesn't happen. So these 2 are in series. But these 2, they are in parallel because they are both between this node. And in a node, you cannot find any resistors in between. So the best here is if we can combine these 2 and 3 first in series. And by the time we add 2 and 3, we now have 6. Sorry, we have 5. 2 plus 3 is 5 because in series we just add. So at the end of the day, this circuit turns to something like this. So here is 4 ohms. Here is 12 ohms. And now this is what? 5 ohms. So sometimes you might need to connect the series first before parallel. Sometimes parallel before series. In this case, we'll join the series first. Then these 3 are now in parallel. Since they are not in parallel, using the formula, the effective resistance R equals to 1 over, you now start doing 1 over 5 plus 1 over 4 plus 1 over 12. So when you take the LCM should be 60. So from here, R total. So we have 1 over, we have 60. 5 and 60 should be 12. 4 and 60 should be, then 12 and 60 should be 5. So this 60 will go up because of this reciprocal. 60 will go up. So R total becomes 60 divided by 50 plus 5, 20. 20 plus 12 is what? 32. So from here, total R equals to 30 over 16, 15 over 8. 15 over 8 ohms. For this second one, these 3 resistors are in parallel, obviously. Why? They are between these 2 nodes. They share the same node. Everything here, here. All their ends, all their terminals are connected together. So for this one, the best is let's do the parallel first, then the series. So let's join this one in parallel. So the total resistance in parallel equals to 1 over, that is 1 over 3 plus 1 over 4 plus 1 over 12. So total resistance in parallel becomes 1 over, the LCM of 3, 4, 12 is 12. 3 into 12, 4, 4 times 1, 4. 4 into 12, 3, 3 times 1, 3. 3 times 1 times 1. So it means all the resistors in parallel becomes, this 12 will go up, that will be 12 over 8. Then from here, it becomes 4 over 3 ohms. That is for all these 3. So at the end of the day, this circuit becomes something like this. Here we have the 2 ohms resistor, and here all these 3 together is now 4 over 3 ohms. So the effective resistance now we just add, since they're in series. That's 2 plus 4 over 3. 3 times 2, 6. 6 plus 4, 10. So the total resistance equals to 10 over 3 ohms. This is the effective resistance. Although when we check here, we have 2, 3, 4, 12. 2, 3, 4, 12. We have 4 equal resistors, but because the arrangements are different, the resistors are also what? Different. So this one is about 2 point something, this is about what? 3 point something. So arrangement is very important and key. This is where I'm going to stop for today. In our next class, still on the circuit, we will now talk about the source of EMF itself, electric cells. So these electric cells, they are source of EMF and they are part of the circuit. So there is a small problem. What's the problem? Whenever, let's suppose we have the external resistor here. Whenever current passes through this external resistor, the current must also pass through the cell itself. So this cell will also resist the flow of current. So it's going to have internal resistance, small r. So meaning, because of the presence of the cell, there will be additional resistance. In all the questions we saw so far, or my explanation, I didn't mention anything about the external, the internal resistance of the cell. So in our next class, we'll talk about cells briefly, then we'll consider the internal resistance of the cell, then we'll now solve questions in general.